Hi.
That's why anti-side comes.
Suvrat and Raju will be concluding these lecture series on the information paradox.
So, thank you very much. I wanted to first start by asking if there are questions from last time that we should address before we go on. Okay. So let me quickly recap what we did last time, and then I'll try and say a little bit more. So this talk will be a little more technical than the other two talks, but I'll try and keep continuity with what we did. I should say before I start that this is based on the following paper. This is work with Kyriakos Lantimos. Ian William Bryan and Toby Bennett. Okay, so these are my collaborators. This is based on a paper that we wrote a few months ago. We also wrote a more recent paper a couple of months ago at the end of last year, which relates to some of the ideas that I discussed, and if I have time, I'll discuss that later. Okay, so remember that at the end of the last lecture, I wrote down this relation that said that phi of x in is related to p of. And so the idea was that somehow a local degree of freedom, a field operator inside the black hole, should be identified with a very complicated polynomial of field operators outside the black hole. And now I'm going to try and make this precise so that we can turn this into an equality. Okay, so the first thing I'll do is in this talk, in fact, even though this is a series of lectures about the black hole information problem, I'm going to forget about black holes and just think about empty anti-de Sitter space. So I'm going to show you how a formula of this kind holds an empty anti-de Sitter space, where we think we understand a lot, where we think we understand the theory very well, and there isn't so much controversy. And so I'll try and show you how, without adding any new physics, a formula of this kind will hold an empty anti-de Sitter space. I should say once more that the important consistency check you should demand when we write down such a formula is that it should be consistent with locality and low point correlation. We'll see that what we get will be consistent. Okay, so let me remind you what empty anti-de Sitter space looks like. We'll just write down the metric. So this is empty anti-de Sitter space. This is a global version of anti-de Sitter space, and R here is the radial coordinate. R equal to infinity is the boundary, and R equal to 0 is the center of AdS. And at each point in R you have a sphere. We can in fact, for the purposes of this talk, just be in AdS 4. So this is an S2 at every point. And this is the time direction. Okay. Now the units here correspond to choosing LAdS equal to 1. So there's a radius of AdS that should enter here. I've chosen LAdS equal to 1. There's in fact a large parameter in our problem because we're going to be talking about gravity. And that large parameter is LAdS by L blank, and I'll call that n. In fact, if you're in AdS 5 cross S5, this would be n to the 1 by 4th. Okay, and if this n was the n of the SUN theory. But for us here, we just want a large parameter, and the large parameter is the ratio of the AdS scale to the Planck scale. Okay? So the AdS scale is much bigger than the Planck scale, and how much bigger is quantified by this number n. Okay. Good. So geometrically, the way you should think about empty anti-de Sitter space is in terms of a solid cylinder, where this is R equal to infinity, and this is R equal to 0. And so there's some boundary of the cylinder. This boundary is a sphere, and then there's a bulk of the cylinder. It's a solid cylinder, and the center of AdS is at R equal to 0. Okay. Now, one thing to recognize is that even though the boundary is at R equal to infinity, if you draw light rays, these light rays can actually cross from one part to the other part in finite time. So the light rays can actually cross over from, if you measure time on the boundary, then light rays can cross from one side of the boundary to the other side of the boundary through the bulk of AdS in finite time, even though it looks like the boundary is at R equal to infinity. In fact, the simplest way to see this is to go to the so-called tortoise coordinates, which are just defined this way. Okay. And then R star is tan inverse R. And using this, you can easily check that the light like geodesics that don't move in the sphere just go along delta R star is delta T. And so you can see that light like geodesics can go and R star is pi by 2, it ranges from pi by 2 to 0, and so light like geodesics can clearly cross the range of R star equal to pi by 2 to 0 in a time which is pi by 2. Okay. So the light crossing time of AdS is pi. So this is just some very elementary statements about the geometry of AdS. Are any questions about this one? Okay. So now what I want to consider first, even though eventually I'll think about a theory of gravity, for now let's just think about a simple scalar field which could have some interactions. But for now let's just take it to be minimally coupled. And so we have a simple scalar field which satisfies this kind of an equation. And of course you can quantize this simple scalar field. You can quantize it just by writing phi as a complete sum so you can solve this wave equation and then you get some radial solutions. These radial solutions are some hypergeometric functions that you can write down explicitly, which I won't write down now. They're not hard to write down. There's of course, T is a Killing vector, so the behavior in T is very simple. It's an exponential. You get some spherical harmonics in the sphere. Now, the important thing to recognize is that, in fact, the allowed frequencies here are discrete. So, even though this is a non-compact space and that R goes out to infinity, for all practical purposes, doing physics in AdS is like doing physics in a box, and therefore the allowed frequencies that can appear here are discrete, and they're given by this 2n. Whereas delta is in 4 dimensions given by delta to delta minus 3, and in general this becomes d for AdS d plus 1. So if I give you the mass of the field, you get some number delta, and that delta and the allowed frequencies of the scalar field are given by this delta plus L, is 2n. L is this L, and 2n is a number. It's just a number. So the modes of the field get quantized in discrete units, and that's because effectively this field, even though it's living in AdS, is like a field that's living inside a box. And because you put some normalizable boundary conditions on the boundary of the box, you're not allowing energy to leak out. Therefore, you get standing wave solutions with discrete frequencies. These discrete frequencies are these ones. Okay. Fine. Now let me say one more thing. You can, one standard part of the dictionary that goes into the AdS CFT correspondence is to say that the boundary limit of bulk operators is given by a boundary operator. So you can define take the boundary limit of this bulk operator phi, you scale up the operator as you go towards the boundary by some positive power of r, because the operator tends to die off near the boundary. That comes by looking at the behavior of this wave function and demanding that it's normalizable near the boundary. If you scale it up, you get some boundary operator, that's the boundary limit of the bulk operator. This in fact is an operator that lives in the boundary CFT, but we won't need that. If you like, for the purposes of this talk, you can just think about O's as being operators that live on the boundary of anti-de Sitter space, but within the bulk theory. So these are just operators that live in the same theory that are obtained by taking the boundary limits of these bulk operators. Okay. Then you can easily check that these creation and annihilation operators that I wrote are just proportional.
modulo large number of corrections, no?
Modulo what corrections?
Large number of 1 over n corrections.
Which one? Which one? This is just right now a definition for me.
Right, but that was a linearized equation. So
This was a linearized equation, but
And
even if
then-
this was, yes,
corresponding to a linearized equation, you want to find a boundary operator.
yes. But
Just,
even if this was not a linearized equation, let me take the fact that this was a linearized equation. I just wanted to get to point out this quantization of frequency is well n is large. But let's say you did not have a linearized equation, there would still be a boundary limit to the bulk operator, and that boundary limit would be this boundary. For this part, the linearized part is not important. The linearized part is important for saying this: if you did not linearize it, you would get some 1 over n corrections to these frequencies. But what I wanted to point out was that at large n, you get a discrete spectrum. So you can check easily that these creation and annihilation operators are proportional. These E and Ls I wrote down are just proportional to the modes of these boundary operators. These O, T, omega operators. That's actually pretty easy to see. If you just take this limit I've written here, it corresponds to taking a limit of these radial wave functions. And the limit of these radial wave functions gives you some number that depends on n and L. And so if you just multiply that number with A and L, you will get O and L. Okay. So there's these two things are just proportional to each other. So these creation and annihilation operators that appear here are the modes of the boundary fields. Is that okay? Now the next point I want to make, which comes from here, is to recognize that if I gave you data over the entire light crossing time, so let's call this minus pi. If I gave you data over the entire light crossing time of the boundary, then you could, if I told you O's, the values of O's for the entire light crossing time of the boundary, then you could Fourier transform O of t omega and obtain O of nl. Right? So if I give you this data, if I give you this much data, that tells me everything I want to know about the bulk operator. Okay. Is this clear? The reason for this is that if I give you O of t, you Fourier transform O of t. You know that the allowed frequencies that appear in O of t have to be delta plus L plus 2n. Therefore, you get O of n L. Okay. You put that into A and L here, and you get the bulk field. And this is now an expression for the field at all points in space and time. So if I give you boundary data on a patch from minus pi by 2 to pi by 2, that tells you everything you want to know about the bulk. There's another way to see this. The other way to see this is to recognize that if you look at the causal wedge of this region. So if I give you this region, this band from minus pi by 2 to pi by 2, and on both sides of course, and you look at the causal wedge of this region, that contains a complete Cauchy slice in the bulk. Okay. So if there's a complete Cauchy slice that runs through here, that's contained in the causal wedge of this region on the boundary. So if I told you O of t, that's like telling me the boundary values of phi of t here, and then you could solve the equation of motion to recover the value of phi of t on this Cauchy slice, and then you would be able to evolve it forward and backward using the bulk Hamiltonian. So if I give you data on this full light crossing time with a band that's this big, I've told you everything there is to know about the bulk field, about this empty AdS background. Okay, so now the question I want to ask is, what if I didn't give you data from minus pi by 2 to pi by 2, but I instead only gave you data from minus t by 2 to t by 2, where this minus t, where t was some number which was smaller than pi? What then have you told me? In fact, it's not hard to see just by this partial differential equation argument, and also by just explicitly solving the wave equation, that if you give me data from minus t by 2 to t by 2, then I can look a certain depth into AdS, and that's not the full depth of AdS. In fact, I can look a depth by, if you give me data from minus t by 2 to t by 2 for O of t, then I can use that to look this deep into AdS, but not any deeper. And there's an entire diamond in the middle. Let me go to different colors. That's causally disconnected from this region, and this diamond I'll call D. So I hope the figure is clear. I hope it's clear also at the back. I hope you can see. So I'm giving you data. I'm telling you the values of this operator O of t omega on a full band on all of AdS from in the region minus t by 2 to t by 2. This band is causally connected to some region in the bulk. That region I call D bar. There's an entire causal diamond D in the interior of AdS, which is completely causally disconnected from this band. And that diamond I call D. Okay. Do you see that? Yes.
So D is just the upper part.
No, D is the full diamond. It's the full blue diamond. It's the full diamond. All of these parts are disconnected causally from here. They're all separated. I'm not drawing it very well, but there's a causal wedge and then there's a diamond which is complementary. Okay. In particular, the point r equal to 0 lives in the middle of this diamond. So this statement, this figure I've drawn here, corresponds to a second line you could write down here. The second line is a statement that if you give me data and just using simple geometry, corresponds to phi of 8, letting me solve for phi of r0 omega for cot t by 2 So if you give me data on the boundary from minus pi by 2 to pi by 2, that's just a limit of this where you take t equal to pi, okay? And then cot t by 2 goes to 0. So it tells me what phi of r at time 0 and omega is for all values of r. Okay. Whereas if you give me data on the boundary from minus t by 2 to t by 2, that gives you only phi of r0 omega for these values of r. Okay. Now why is this a problem that's worth considering, and why is this related to black holes? The reason this is related to black holes is that by artificially restricting the observer to this band in the boundary of finite thickness, we've basically stopped the observer on the boundary from being able to look past this horizon. So by fiat, by demanding that the observer restrict her observations to the region which lives from minus t by 2 to t by 2, we have in a sense created a black hole in the bulk. Okay. There's no black hole in the bulk. Okay. This is just empty AdS. But by forcing the observer to restrict his or her observations to this band, okay, we've prevented the observer from being able to look past this horizon. So there's a part that the observer looks like the observer cannot access if the observer is given only data about the boundary on this region. So this is it's a very, very simple toy model of a black hole. It says that I'm going to restrict you to some time on the boundary, and for some reason I'm going to allow you to make observations only in this time band. If I allow you to make observations only in this time band, then naively using the bulk equations of motion, using just naive causality, it looks like observations in this time band correspond to observations in the bulk in this region D bar, but don't tell you anything about what's happening in D. That's because D is spatially separated from this band. Okay? So this is a toy model of a black hole. Is that clear? Okay. Now what I want to show here, and the object of the rest of the talk, is to show you how the field phi of r can in fact be written in terms of operators that live only inside this band. So the object of the talk is to write phi of 0 t equal to 0 omega in terms of So this is the objective of the talk. And we'll see that what we'll get out is that we'll find that this phi at r equal to 0 is a very complicated polynomial of operators that live on the band. And that will give us an explicit example of the complementarity proposal that I mentioned previously. Okay? So do all of you agree that at least that if I was able to do this, if I was able to write down a formula, then it would give me explicitly a realization of a situation where a field operator in the middle of AdS is being written in terms of a number of other field operators that are all uniformly spatially separated from the operator. Okay. And that was the essence of the proposal of complementarity. It was a statement that you could write an operator in terms of in a theory of gravity. This can only make sense in the theory of gravity. You can write an operator in terms of a number of other operators, all of which are uniformly spatially separated from the original operator. So if we succeed in this, as I'll show you, this is a rather simple construction. By the end of this construction, we will have got a concrete example of the kind of argument I made previously.
So you always use phi to satisfy this linear equation, right? Then we know.
No, actually I will not use phi to satisfy. I'm not going to use this. Nothing in the argument will depend on the fact that phi satisfies a linear equation. Everything I'll say will generalize if phi had interactions.
Okay, no, but I was asking you something very naively.
Yes.
If phi interact with gravity to
Yes.
change the metric in the background and so on, then the light cones I draw would be different. So then I wouldn't know whether it was outside the light cone or not.
No, so this.
I can't both use empty AdS and also assume it has gravity.
Correct. But the formula I'll write down. So the formula I'll write down will in the end say that phi at r equal to 0 is some complicated version of phi on the boundary. If I insert that operator into correlation functions about empty AdS, that operator looks like it obeys all the causality that it does in empty AdS. So there's no contradiction in saying. In fact, this is an important aspect of complementarity. It's a statement that the final formula that you get should respect bulk causality within low point correlation functions. So within low point correlation functions, they should resemble everything that you have in empty AdS. But there should still be some ultimate relation if you look at the full theory. But low point correlation functions look exactly the way they do in empty AdS. So otherwise, you're right. There's no point in talking about a space-time. But the reason I insist on talking about a space-time is because low point correlation functions will look the way they do in empty AdS. But there will still be a relation which will involve polynomials of order n, which will give me this
But
relation.
I was just asking, I should probably let you go on first.
Yes.
Maybe I can just put the questions and you can come back to it.
Yes.
If the n is big enough, so the operator is heavy enough to distort the light cone enough.
Which operator is heavy enough?
The final one when you choose.
It won't be a heavy operator.
that's what I
So yes.
So it won't distort my background.
No, it won't. So you can tell me when I write down the final formula if you disagree with
So
anything.
that's fine. If it doesn't
Yes,
distort
if there's
the
some
light
aspect I've not, yes. So yes. So let me write down the final formula and then you can tell me if there's some aspect I haven't. Okay. So first, let's say something trivial. So by the way, I should say this about the equation of motion. At various points, this equation of motion is kind of simple to use. So I used it to motivate this discrete spectrum. But in fact, nothing I say is actually dependent on the fact that phi obeys an equation of motion. So in fact, as I go on, I'll say some statements. I'll use the fact that the Hilbert space is an approximate Fock space, which is true at large n, and we are working at large n, and there's no problem with that. But everything I say, in fact, will generalize beyond that, and I'll point out how. Okay. So first, let's take phi, and let's just expand it in a basis of states. Okay. So let's take this operator phi. I'm just going to call it phi of 0. Okay, by phi of 0 I mean this. Phi of r equal to 0, t equal to 0. I'll just call it phi of 0 to save myself a lot of writing. And by the way, right now what I'm writing down is totally tautological. And I expand it in a basis of complete states. No, you could be interested in everywhere else. Everything I say will be. Just to make it most dramatic, but it's the one that's most separate. Yes, everything in the diagram can be. Okay, so phi of 0 is written this way. This is just an expansion in the complete basis of states. If I give you a specific basis of states, for example, if I give you the basis of states that are created by modes of that operator, that are created by these creation and annihilation operators, I can work out what these Cij coefficients are explicitly. They are again something you can work out from effective field theory. And clearly this operator that you write down, is so when I say you work out the Cij coefficients, you work out the Cij coefficients just by quantizing the field in bulk in the bulk area spacetime. And so it's a field that explicitly obeys whatever constraints of causality that quantum field theory in curved spacetime obeys. Okay. Now let me say a little bit about these coefficients Cij. The first statement is that, as we've discussed already a couple of times in these lectures, you see, localizing a point at r equal to 0 is something which is something hard to do in gravity, and that's because the metric fluctuates in gravity. Okay? So if one way to define this point r equal to 0, for example, would be to say, I shoot a point from here, I shoot a ray of light from here, from the antipodal point. The point where they meet is the r equal to 0 point. Okay? But that's something that works, that makes sense only at leading order in 1 by n. If I start considering fluctuations for the metric, then it's clear that that's something that, there are many different ways of defining r equal to 0 classically, and they're all inequivalent at a quantum level. And so it's not clear what r equal to 0 means at a quantum level. So that's the statement that these Cij coefficients are defined only up to order 1 by n. If you give me a specific prescription for defining a local operator, I can also tell you what these coefficients are at a higher order, but they don't have a good gauge invariant meaning beyond order 1. So there's a simple gauge invariant meaning of these Cij coefficients at order 1. At order 1 by n, what you mean by these coefficients depends on how you define the point r equal to 0, which depends on what prescription you use to fix things, and that's not a good gauge invariant prescription. So I'm only going to be interested in these coefficients up to terms of order 1 by n. Secondly, even though in principle this runs over a complete set of states, I'm only going to be interested in the low energy parts of this expansion, so I'm going to truncate this from vacuum to some value which is of order n. Okay. So I will never consider the matrix elements of this operator for heavy energy eigenstates that are of order n. That's because I want to think of an operator that you define in effective field theory, where you don't understand very well the matrix elements of this operator between heavy energy eigenstates. Okay. And this again, doesn't make any difference within low point correlation function when you never produce these heavy energy eigenstates. So I'm going to look at a truncated expansion, and I'm only going to worry about these coefficients up to order 1 by n.
And is the number of particles, number of icons.
N was, capital N is always LADS by n. Okay, good. So now in the large n expansion, okay, and I'm going to make an argument in the large n limit, and then I'll tell you how it generalizes away from that. In the large n expansion, these states that appear on the right hand side have the structure of a Fock space. For example, the set of single particle states that you get are states that are created, by the way, small n and large n are different, so please don't be confused about that. Are created by taking one of these creation operators, these operators. Also, by the way, I'll now suppress the L mode everywhere, so the L mode is going to vanish because it won't play a role in what I say. So by taking one of these creation operators and acting on the vacuum, so this gives you a set of single particle states. You can act with two creation operators, and that will give you a set of two particle states, and so on. Once again, I never want to consider more than capital N particle states. Okay. Now, you might have thought that to create this mode, you need data for O of t all the way from minus pi by 2 to pi by 2, because what is On after all? On is just integral O of t into e to the int from minus pi by 2 to pi by 2. Right? So you might have thought that to create the single particle state, I need to use operators that go all the way from minus pi by 2 to pi by 2. That's because this single particle state is created by Fourier transforming the boundary operator from a region minus pi by 2 to pi by 2. Okay. However, the first statement is that in fact you can create this n as integral O of t, f of t, and t on the vacuum, where this f of t has support only in this band minus t by 2 to t by 2. Okay. So one way to say it is f of t has support, or by explicitly doing the integral only from minus t by 2 to t by 2. This is a version, by the way, of what's called the Riech-Leader theorem in quantum field theory. So this is the statement that you can create all states in the Hilbert space by acting with states that live only on this. So if you think of this in the bulb, this is the statement that you have this part of the Cauchy slice, which is an annulus, and by acting with operators in the annulus, you can create, the space that you get is dense in the full Hilbert space of the quantum field theory. And this is a statement you can prove in quantum field theories without making any assumption about the equations of motion, and it's called the Riesz-Leiter theorem. What I'm saying here is a very simple version of the Riesz-Leiter theorem, and I'll prove it for you. Okay. So now you might say, how could this happen? How could it be that you can create this state by just acting with the band minus t by 2 t by 2? But in fact, that's not hard, and I'll prove it by contradiction. So let's say there existed psi, okay, which you could not create in this way. Then it would be the case that psi would have some part which was orthogonal to all states that you could create in this way. Because there's some state which you can't create in this way. So there's some psi which is orthogonal to all states you can create in this way. That means that this is equal to 0 for all f of t, which has support from minus t by 2 to t by 2. So I'm trying to make the argument by contradiction. Let us say there existed a psi which can't be written in this way, some linear combination of the ends. Then that means that this psi is orthogonal to all states which can be created in this way. Therefore, this inner product is 0 for all f of t with support in minus t by 2. Okay. So in particular, this must mean that omega O of t psi, whatever the state psi is equal to 0 for all t Okay, but if this is the case, then you have a complete basis of states. This you can expand as omega O of t. So I can say this. And this expression, you can just write as omega O of 0 Well, the only energies that appear here are positive energies. So I've just taken this and I've expanded it out in a complete basis of states, and I've used the positivity of the Hamiltonian. So the ground state has 0 energy and everything else has positive energy. So the only energies that appear here are positive energies. If this is the case, then this function O of t f of t is analytic, okay, which is 0 for minus t by 2 to t by 2, is also analytic in the lower half plane. So I have a function here which is 0 in this interval minus t by 2 to t by 2, and it's analytic in the lower half plane. In fact, that tells you that the function is 0 everywhere on the real line. So if I have a function which is 0, this is what's called the edge of the wedge theorem sometimes. But if I have a function that's analytic on the lower half plane, if it's 0 here, and if it's analytic in the lower half plane, I can in fact continue the function from here to here through the lower half plane, and I can prove that the function is 0 everywhere on the real line. So if I have a function which is analytic and which is 0 on some part of the real line, then it's an analytic in the lower half plane, then it's 0 everywhere. That means that if this function is 0 for all t in this region, then by this argument, this means that this inner product is 0 for all t. So the arguments I made tell us that assumption, which was that f of t will support in Thus, the analyticity argument actually implies that this is 0 for all t. Okay, but if this is the case, this means that psi is 0. Okay, because there's no, all states in the theory can be created by acting with the vacuum, acting on the vacuum with O of omega. So if this is 0, that means that psi is 0. Okay? And therefore, there is no such state. That means that no such state exists which is orthogonal to all states that can be created in this region. Okay, so this is once again an example of, as I said, the Riesz-Leiter theorem, which was proved using very similar techniques in a full quantum field theory. And what you require actually are some analyticity properties of the correlation function, not really any assumptions about free field theories. Sometimes this statement is colloquially stated by saying that you can create the moon in Alpha Centauri by acting with an operator in this room, and that's true. And that's because if you allow me to act with arbitrary Hermitian operators in this room, I can indeed do whatever I like. I can use the entanglement of the vacuum to create the moon somewhere else. This is not by itself a violation of causality, and it doesn't require anywhere the notion of gravity. It's not a violation of causality because really, when we talk about causality, we are only allowed to act with unitary operators. We are only allowed to make unitary transformations to the state. And if you make a local unitary transformation to the state, then of course you can't change the density matrix of any space-like separated region. This is something you can check just by playing around with EPR pairs. If I give you an EPR pair, and I allowed you to act with arbitrary Hermitian operators on one part of the EPR pair, I could indeed change the density matrix as seen by the other observer. But that's not what you're allowed to do. What you're allowed to do is act with arbitrary unitary operators on one part, on one spin, and that indeed leaves the density matrix of the other observer independent. Okay. So once again, the statement here is that you can create all states in the theory by acting with operators that have support only between -t/2 to t/2. This is a specific version of the Richtlieder theorem as used in quantum field theory. It's not by itself in contradiction with causality.
So can you put commutators then? I mean, if you have commutators at two space-like points,
Yes.
those are supposed to be exactly zero.
Those are here in this case, they're absolutely exactly zero.
So the commutators are zero.
So far I haven't said anything non-local. What I've said would hold exactly in a quantum field theory in AdS. It would hold in quantum field theories in our space. There's no gravity
So what
here.
you said about here, what does it mean for commutators at two different points? It doesn't say.
It doesn't say anything about commutators right now. The commutators would be exactly zero in space-like points. There's nothing so far. I haven't even added gravity here. So this statement would hold in a scalar field theory which obeys microcausality non-perturbatively, and this statement would still be true.
Is it even true for something as simple as ordinary quantum mechanics or model vector?
This is a statement about quantum field theories in the vacuum. So the statement is that if you take a finite energy state in the quantum field theory, that has sufficient entanglement to allow you to do this. So this is a statement about, this statement is really a statement about entanglement of a quantum field theory vacuum. So all finite energy states in a quantum field theory have this property that you can create arbitrary states in the Hilbert space by acting with local operators in the region. But it's not a statement that's true for quantum mechanics of a single electron. It's a statement about quantum field, vacuum and local quantum field theories. So yes.
So all of this holds if we take t to 0?
All of this does hold if you take t to 0, it's true. But I don't want to take t to be smaller than 1 over n, because then then these functions f of t I would have to take would have to have oscillations over a region 1 over n. So you're right, there's nothing here which requires t to be large, but I don't want to I want to take t to be larger than 1 by n. Okay. Okay, are there any other questions about this? Okay, good. So let's just see what we've obtained. What we've obtained so far is we've taken this expression. And by the way, I made the argument for single trace operators. Obviously, a similar argument holds for double trace and arbitrary trace operators. In making this argument right now, I'm trying to divide operators into single particle and multi-particle states, which is a good thing to do at large order when you're at large n. But in general, as I said, there is a theorem in local quantum field theory that guarantees, and the theorem is really that the vacuum is both cyclic and separating with respect to the algebra of operators in this happiness. Okay, so there's a theorem in quantum field theory that tells you this would go beyond the 1 over n expansion. I don't need it. Okay. Okay, so what have we achieved so far? So what we have achieved so far is that we've written this expansion in this form. These xi's and x datas are simple polynomials in O of E. So far what we've achieved is the following. We had an expansion that was written in terms of a complete set of states. Initially, the basis we decided to choose for the complete set of states was based on states created by acting with operators in the full range, okay, by acting with creation and annihilation operators of O of T. What this Richter theorem tells us is that in fact you could create all states in the Hilbert space by acting with operators that are only, that only involve insertions of O of T in the region minus T by 2 to T by 2. Second, these xi's are simple polynomials. Okay? In fact, remember in the theorem we just proved, if you had a single particle state, you could create that with another, just a single trace operator, suitably smeared in the region minus T by 2 to T by 2. So you could take a single trace operator and suitably smear it, not with e to the minus I and t, but with some other function f and t, which actually you can work out explicitly. So if you look at our paper, we worked out what these functions are explicitly. But the theorem we proved is that there exists a function fn of t that has support only on minus t by 2 to t by 2, so that when you smear the operator O with it, you can create the same single particle state that you would have created by acting on the larger band. And so these xi's are simple polynomials, because the only states that appear here are single particle, multi-particle, and higher particle states, but we've cut off the energy of states at n. So n particle states never appear, and therefore these xi's are all polynomials which involve less than n insertion. So far this is what we've shown. Of course, so far nothing is surprising, and nothing involves gravity anywhere, and so nothing involves any loss of locality. This is a surprising statement, but it's a statement that holds in all quantum field theories. There's no loss of locality. And that's because we haven't managed to write the operator at 0 in terms of operators here, and that's because there's this vacuum projector that's sitting in the middle. What we've managed to say is that the action of the operator at 0 on the vacuum can be mimicked by the action of an operator on the boundary at a point which is spatially separated from it. But that's not the same as saying that the operator can be mimicked by an operator elsewhere, right? Because there's a vacuum projector. Okay, so the next thing we have to do is somehow find a way to write down this vacuum projector in terms of operators that live in this band. Okay, now this is something that's possible only in the theory of gravity. And in fact, it's very simple, and the simple fact we need to use is that in a theory of gravity, and only in a theory of gravity. Anyway, sorry, before I go on to gravity, are there any questions about this part? Yes.
So since they're between minus t over 2 and t over 2, you say you kind of like creating a horizon.
Yes, in a sense, yes.
Yes. Does it still make, can you still speak of like part of AdS as being empty? Why is
Yes.
it created that?
No, it's not created a horizon in any physical sense. You haven't injected any energy. It's just, you've just restricted the depth to which you can look by restricting the range to which you can move in time on the boundary. You've restricted the depth to which you can look. So this is a horizon by fiat. It's almost a horizon by saying, I tell you that you can't look beyond a certain region. You see, if I restrict you to this region from minus t by 2 to t by 2, it's the same as restricting you to operators in this region, this green part, and the operators in this part are all spatially separated from operators in this band. You see this? So if I restrict you to operators in this band, I've created a horizon by fiat, because I'm just telling you can't see these operators because they're spatially separated from you. It would be like creating a Rindler horizon, if you like. You can always move in a certain way so as to make some part of the space-time causally separated from you. That doesn't mean anything physically has appeared in that part of space-time. It just means that you have chosen a certain world line which separates some part of the space causally from you. In this case, this is not even a world line. It's just an observer who is born at minus t by 2 and dies at t by 2, and therefore can't see anything beyond that. So you haven't done anything physical to the space-time. All you've done is you've restricted the abilities of the observer. So it's like Rindler space, if you like. You can have an uniformly accelerating observer. That doesn't mean a horizon is really created there. Is that clear? Okay.
What will you not be able to do with this 5-0? I mean, you won't be able to.
What will I not be able to do with what 5-0?
With 5-0 that you have created in this way by applying operator only within this particular.
No, this is still the original expression. This is an identity right now. this is not writing the operator phi or 0 in terms of operators in the band. There's a vacuum projector in the middle. This identity holds in all quantum field theories, with or without gravity. This identity does not violate locality. This identity is also not our final end product, because we have not written phi or 0 in terms of operators in the band. What we have written is we have written the action of phi or 0 on the vacuum in terms of the action of simple phi or 0 operators in the band on the vacuum. That's not the same as writing one operator in terms of the other. Okay? So the Riche-Leiter theorem tells you the action of all operators in the vacuum can be written in terms of the action of any other set of operators in the vacuum. That's just true in all quantum field theories. It just involves some entanglement in the vacuum. It does rely on entanglement in the vacuum.
Such similar statement true for like some other pure states as well? We were not
It's true for all finite energy states actually. All finite energy states have entanglement in the vacuum. So not just the vacuum, but it's true for all finite energy states. Okay. Okay, any other questions? Okay, good. So now we want to complete the final part, and the final part involves necessarily a theory of gravity. And that's because in a theory of gravity, we have something very special. We have something very special, which is that the Hamiltonian in a theory of gravity is a boundary term. Okay? All of you know this anyway from the fact that there's a Gauss law in gravity. So you can always measure the energy of some excitation just by going to infinity and measuring the fall off of the gravitational field at infinity. So there is something special about gravity, and what's special about gravity is that the Hamiltonian is a boundary term. Okay. So of course we can write this down more explicitly. Okay. What we do is you can take anti-de Sitter space, and anti-de Sitter space you can do the analog of what's called the 3+1 split in anti-de Sitter space. So you can write the metric of anti-de Sitter space as just to differentiate it from the n I've been using so far. Okay. And then you can define a stress tensor for the boundary. The stress tensor is defined by looking at the extrinsic curvature of the boundary, and it's basically defined as the gamma mu is this metric that appears here, and then you have to do some subtractions, and these subtractions have been worked out in great detail for anti-de Sitter space, okay, where this theta mu is just del mu, okay, where this is the outward normal to the boundary. Now, and the Hamiltonian is just given by doing the integral of the stress tensor of this field. Okay. This actually, there's some formulas I've written down, but in fact you don't need to think about the formulas, the detailed aspects of the formula so much. Just remember that the energy in gravity, in fact the definition of the energy in gravity, is always given by looking at the fall off of the field at infinity. Okay? So for all of you who've seen the discussion of either the ADM mass in flat space, or any discussion of canonical quantization of gravity, remember that it's not possible to define the local energy of an object in gravity. Okay, that's not a well-defined thing. The only thing you can talk about is the global energy of something, and how do you define that? You go to infinity and you measure the fall off of the gravitational field. If you do that very carefully, you get some complicated formulas, but you don't need to worry about the exact formulas. The essence is that you just look at the fall off of the gravitational field. The fall off of the gravitational field gives you the Hamiltonian. And that's the definition of the Hamiltonian in gravity. This is something that's true only in a theory of gravity. It's not true otherwise, that the Hamiltonian is a boundary term. In general, the Hamiltonian is a bulk term, but in gravity, it's a boundary term. And in fact, it's this Hamiltonian that's dual to the CFT Hamiltonian. So when we say there's a Hamiltonian for the theory, which is the CFT Hamiltonian, in the bulk, that Hamiltonian is this guy. Okay, good. So now we've said something about gravity, and so here's what the next statement is, that this projector in the vacuum we can write in terms of the theory of gravity in the following way. projector onto the vacuum. So this projector onto the vacuum is just by definition, limit as alpha tends to infinity of e to the minus alpha h, where this is the boundary Hamiltonian. Because you see this action, so by the way, you should always define these subtractions that appear here to ensure that the energy of the vacuum is 0. Okay, so I'm choosing the convention where I've taken these subtractions to ensure these counter terms to ensure the energy of the vacuum is 0. Then you see that this limit gives you 1 on the vacuum, gives you 0 for all states that are higher than the vacuum. Remember also that there's a gap in AdS. Okay. So it gives you, it's not like there are some states which go all the way down to 0. This is an operator which gives you 1 in the vacuum and 0 everywhere else. Okay, so it's a projector onto the vacuum. Okay, but in fact, we can write this projector onto the vacuum as we can approximate it up to the same approximation we used here. Up to the same approximation where we don't want to look at states with energy higher than n. We can approximate this projector as in terms of operators that live on the boundary and in terms of a simple polynomial. And how do we do that? We just expand this. Factorial. Okay. And we put a cutoff here, which I'll discuss in a minute, and we just take alpha to be large and finite. Okay. So here's a polynomial, which I'll write with a p tilde. So p tilde 0 for large alpha pc approximates p0. Okay. So I've written down a polynomial which is just the expansion of this exponential, and I'll now tell you what large alpha and pc, how large, where this pc is, sorry, this cut off, there are lots of p's. Let me use nc, sorry. Okay, sorry. I have too many p's to change to n. So sorry, there are many p's here. There's a p0 tilde, which is the polynomial approximation to the projector onto the vacuum. There's this p0, which is the exact projector onto the vacuum. And there's a small pc, which is the cutoff. So the statement is this polynomial approximates this projector very well, provided we take alpha and pc to be large. Let me just try and tell you how large we have to take alpha and pc to be. The first question is, remember that AdS has a gap. AdS has a gap, it's the first thing we wrote down, and therefore the lowest energy states that appear in AdS have energy of order 1. Remember, the lowest energy states that appear here, the energies of the states that appear here are quantized in units of a delta plus L plus 2n. So the lowest energy that's allowed here is delta, where delta is a dimension. That's some order 1 number. Okay. So if we take alpha to be large enough so that all states which have energy which is not 0 are suppressed by a power of 1 by n, okay, that's sufficient to the approximation we are working here, which is an order 1 by n approximation. Okay. So let's take alpha to be log n. Yes.
Switch the glow marker.
Oh, sorry. I think the glow marker has also faded. Oh no, it's not. It's working. This is it. It's regained life. So let's take alpha to be log n. If we take alpha to be log n, you see, if you put an e to the minus alpha here, you get e to the minus log n into h. But the lowest eigenvalue of h, which is not 0, is some order 1 number. So the number you get here is e to the minus some number which could be 4, delta could be 4 or delta could be d in AdSD, is e to the minus d log n, which is 1 by n to the power d. So taking alpha equal to log n ensures that you don't really have to take alpha to infinity. If you're working to leading order in the 1 by n expansion, you can just take alpha to be log n. And that's already enough to ensure that this polynomial, this p0 tilde, approximates p0 up to an 1 by n. So let's take alpha to be log n. How large do we have to take this cutoff to be? You see, when can you approximate a polynomial when can you approximate an exponential by a polynomial? If you want to approximate e to the x, you should approximate e to the x by a polynomial that contains at least x terms. An exponential is well approximated by a polynomial that contains as many terms as the exponent. Okay. So this is well approximated by some term, by something of this kind. You can take this cutoff to be 10 times x if you want to get good accuracy. Okay. But as long you have to keep at least x terms in order to be able to approximate this exponential well by polynomial. That's easy to get. What's the largest exponent that can appear here? See, not only do we have an IR cutoff, the fact that alpha was equal to log n came from our IR cutoff. It was the fact that there was a gap in the theory and the lowest excitations had AdS scale energy. We also have a UV cutoff in the theory. The UV cutoff in the theory is n, it's what we put in here. Therefore, the largest exponent that can appear here is n log n. In fact, it's much smaller than n log n if you put a UV cutoff that's much below n. And therefore, we take Pc to be n log n. With these values, alpha is equal to log n and Pc is equal to n log n, this P0 tilde gives us within all low energy states, within all states that don't have energy n, it gives us an excellent approximation to this projector P0. But now notice that this projector P0 tilde is a complicated polynomial in operators that have support only in this band. That's because it's a complicated polynomial in H, but H is just the integral of the stress tensor, which is just given by a limit of the boundary graviton. So the boundary metric, some normalizable fall off of the graviton is what gives you H. That fall off clearly is something you can define just at t equal to 0. You don't even need this minus t by 2 to t by 2 range. Okay? And therefore you have written P0 tilde as a polynomial in operators with support only in this region minus t by 2 to t by 2. Okay? So this P0 tilde, actually it's explicitly a very complicated polynomial. You see, it's very complicated. Now I've even quantified very. It's very complicated in that it has n log n terms. Okay, now we're done actually, because all we do is we replace this line with what we have here. So I'll just convert this. Okay, so you see now I have written phi of 0, I have derived the fact that phi of 0, can be written as the following, made up of the following ingredients. Some coefficient Cij that can be worked out from bulk effective field theory in AdS, and which we can work out explicitly. Some polynomials xi that are simple polynomials that come from the Riesz-Leiter theorem. And a projector which is a very complicated polynomial, which is what we worked out here. Okay. And once again, these polynomials have come from the Riesz-Leiter theorem. And this whole identity holds to order 1 by n, but that's okay because that was the initial approximation we had. Okay. So this is an identity now, and this is a statement that gives us an explicit realization of what we wanted previously. Because everything on the right hand side here is a polynomial which has support in minus t by 2 to t by 2. Xi's by construction has support in minus t by 2 to t by 2. P0 tilde by construction has support in minus t by 2 to t by 2. And so does this xj. Okay. And Cij's are just some C numbers. So we have explicitly written an operator in the middle of AdS in terms of operators that live on the boundary of AdS. It's a polynomial. So this gives you an explicit realization of the formula I mentioned at the beginning, which was if you write phi of 0 as a complicated polynomial of operators which are all spatially separated from it. Okay. Okay, let me say a little bit. Are there any questions here? And I want to make a few final comments. Yes.
Is this the only thing that you want to reproduce? Don't you want like the operator? You should also able to reproduce the action of the operator, not only just the vacuum state, but
We do reproduce the action. So you see, this is an expression for the operator. It This reproduces the action of the operator not just in the vacuum state. This is the expression for the operator. This expression on the right hand side reproduces the action of the operator not just in the vacuum. This is the full operator. Now I've derived the full operator. I certainly have not, there was, at this level, I had derived only the action of the operator in the vacuum. Okay. Once I've inserted this polynomial, I've written an identity of phi of 0 is equal to this. So this reproduces the action of the operator on all states as long as they are not states of energy higher than n. So the approximations I made here were here in ensuring that no states with energy higher than n entered. And the approximation I made here was a 1 by n expression, but this is an equality. So it was not clear and not understanding.
And isn't your result stronger than what you wrote? It should be polynomials of the energy momentum tensor.
Is what?
Polynomials of energy momentum, no?
So there is a polynomial of the energy momentum tensor that enters here.
And there are
That's
other,
this.
and
then there are other operators which are polynomials of the phis itself. So it's not, these xi's were things we introduced at the beginning. They came from the Rief-Leiter theorem, and they involve also other operators. They involve the same phi operators and t. So these xi's involve phis, these phis at this point?
Only the phi.
Only the phis. So this is a combination of the phis and the stress tensor and the phis again. But let me say again, they involve only the phis at leading order in 1 by n. But yes, at leading order in 1 by n, they involve only the phis. So this result is that it's phi, there's some polynomial stress tensor and phis again. There's some combination. Okay, so let me just say a little bit more. So let me give you another picture of what we've done. First of all, let me make a few more comments. About 10 minutes more? 10 minutes more.
I think we started at 10 past, but we can go.
We started at 10 past? Oh.
I believe so, but we can go.
Oh, sorry, 5 minutes more. Sorry, apologies. I've gone over time. Okay, let me end 5 minutes more. Okay.
So we have dinner at 7,
Yeah.
so keep going as long as you want.
No, I'll just take 5 minutes more. Okay, so you see what we've done here, I'll just give you another picture. Okay, so we have this operator phi of 0, and we have these operators in the annulus, in the boundary. Okay. So this is the picture I should have drawn in the beginning. But we've written phi of 0 in terms of operators that live in this annulus. So this, instead of thinking of operators in this band minus t by 2 to t by 2, I could also think of operators in this part, which was the annulus. So what we've done here is written phi of 0 as complicated polynomial of operators in the annulus. Okay. That is because operators in the band and operators in the annulus are related by a simple linear transformation, which you can just work out by solving the partial differential equation. So by proving that we've written phi of 0 in terms of operators in the band, we've also proved they can be written in terms of operators in the annulus. This annulus has the boundary at r equal to infinity, and this is r equal to cot t by 2. Okay. So the inner boundary is at r equal to cot t by 2, and the outer boundary of the annulus is at r equal to infinity. And this annulus is linearly related to this. So if you wrote it in this way, you would change the form of these operators xi. Okay. But you could also do this as one statement. Secondly, remember I said at the beginning that it's very important that whatever version of complementarity we get must be consistent with locality and low point correlators. Here that's guaranteed to us because we started with an expression Cij, where these Cij coefficients were derived using local bulk effective field theory and were guaranteed to obey locality and low point correlation functions. Okay? They were guaranteed to obey locality up to order 1 by n. So we started with an expression which was guaranteed to obey locality, and we've derived another expression which is equal to the original expression. So we see that this expression is also guaranteed to obey equal locality. This is an equality of expressions. So we see that the check that we needed, which was that this expression should obey locality and low point correlators, here it's satisfied because we started with an expression which obeyed that by construction. Because theseCijs were chosen by using bulk effective field theory and ensuring that locality was obeyed, and then we've derived that this is equal to this.
And Suvrat, just one question: can you replace n by m?
This n by some m?
By m.
Well, what is m?
Any number. Any large number.
It's a yes, a large number, but you
Yeah.
want to. It's a question of where you put the cutoff.
That's right.
So you shouldn't. It's a question of
You
how
didn't
high
have to
energy
choose
states you.
M to be N.
You don't have to choose n to be n. You can replace it by m. It's
Yeah,
true.
yeah.
But you don't want to put the cutoff too low, otherwise you would lose
No, no,
locality.
right.
So you do have to take m to be very large. You shouldn't truncate operators. You shouldn't put your UV cutoff too low.
That's right.
So you should take a UV cutoff to be high enough, but it doesn't have to be exactly n, of course. You could take it to be square root of n. Okay. So that's one comment. Good. The second comment is the statement looks kind of surprising. Okay, it looks kind of surprising, but there's a very simple way to understand the statement. Remember that the set of operators in the CFT at one given point of time is complete. If I just give you the set of operators on a time slice at t equal to 0, that is a complete set of operators in the CFT. So that set of operators also includes the operator phi of 0. So it's not surprising that you can write the operator phi of 0 in terms of operators that live in this band. Okay, because the set of operators, even at a single point of time, if I tell you everything I know about the CFT, I've also told you everything I know about the bulk. Okay, not just in parts which are causally linked to the boundary, but also everywhere in the bulk. So in a sense, if you know from AdS CFT, the statement is not surprising. That's the second. Third, you could try and ask, and I won't say I have any more details about this in this talk, but you could try and ask, can you write down a similar formula in flat space? So the answer is no, we don't know how to write down a similar formula in flat space, partly because we don't understand this IR cutoff well enough. One of the things that went into this formula was the IR cutoff. But we do have indications that a similar formula should work in flat space. And the indications are as follows. Let's say I didn't know how to derive this formula. Even before I derived this formula, I could have guessed that a very complicated polynomial would put locality into trouble. And that's because locality in AdS CFT is known to be tied to the 1 over n expansion. And if you start considering polynomials that have n terms, then these polynomials, for such polynomials, the 1 over n expansion breaks down. Okay? So what is the analog of this breakdown in flat space? In flat space, the analog is, there's no value of n, but nevertheless, gravitational perturbation theory dynamically develops a dimensionless parameter, and that parameter is the dimensionless energy divided by Planck scale. So the breakdown of gravitational perturbation theory is the analog of the breakdown of the 1 over n expansion. So in a recent paper with my student Sudeep Ghosh, we tried to analyze the behavior of string perturbation theory for a very large number of particles, and we found that if you take the number of particles to scale with G string, okay, so that if you take the number of particles to scale with G string, then even if the energy of the particles is low, string perturbation theory breaks down, and that might indicate, it doesn't prove of course, but in fact it breaks down precisely at the point where you expect these complementarity effects to enter in if you put in numbers for flat space black holes, and that might indicate, doesn't prove of course, that a similar formula might hold also in flat space. Okay, so that's all I have to say, and we can have more questions and discussions after this. Okay, so I'll stop here.
Any questions?
Yes.
Okay, maybe I could just ask them.
Yes.
I'm not sure I completely understood everything you said here, but suppose at the end I just want to know what is a typical non-local effect I could try to measure. So we have a theory of gravity, that's what you mean, right?
Yes.
And so in this room, if I take two causal separation points,
Yes.
am I supposed to be able to measure something which is non-zero outside the line? Correct?
Yes.
What's an example?
So the example would be that you take a point here, you take a sphere that surrounds it. It's not just 2 points, but you take a point here and you take a sphere that surrounds it. You take a suitably complicated polynomial in the sphere. I don't know what the numbers you have to put in would be, but you take a very complicated polynomial of operators in the sphere, and that polynomial reproduces for you the action of operators in the middle of the sphere. So this number probably has to scale like Planck mass divided by or radius of the sphere divided by Planck scale to some power. So that's at least 10 to, I don't know how big you want to take a sphere to be, but you have to take some 10 to the 35 point or 10 to the 40 point polynomial of operators in the sphere, and then you measure the commutator of that polynomial with an operator in the center of the sphere, and you'll find it's non-zero.
So I don't quite know how to measure commuters, but I was just asking, like, suppose I flash a torch in the middle of this room.
Correct.
That's my operation. I just do
Correct.
something like that.
Correct.
Then before light could have reached there,
Yes.
if I try to do this very complicated measurement, which I'm happy to do,
Yes.
I have some detectors put in a very complicated pattern,
Yes.
but I set off an explosion here,
And they will know.
but before light could have reached there,
Correct.
they would actually
They
find
will know
out.
about it. That's correct.
So with enough photo detectors surrounding
Put
this
in the
point,
sphere, correct.
I can actually check a
With
violation of the speed of light.
10 to the 40, with 10
Yeah,
to the 40
with 10 to
photo
the 40
detectors,
photo
which
detectors.
include, right, so that should involve gravitational effects, yes. So if you were to use fundamentally gravitational effects, you see, it's not so surprising, because in the end, you see, you can't really create any energy in the middle of it. You know, whatever you do, whatever energy you get, that flash of light that you did, you know, was in a sense already,
But I don't
the
think
energy was
can I
already.
do it in the room flat space? Like,
Yes, you can do it in this room in flat space. So the claim that, you know, first of all, these operators were at infinity. So if you wanted me to write down the Hamiltonian in a sphere, I would have to work a little bit harder. But I think you could probably do it. You could take a large enough sphere and you know, write down a similar formula, which would give this. As I said, the key thing is how large you have to take this alpha to be, and for that you need an IR cutoff. I imagine that for the excitations you're looking at, the IR cutoff would be the radius of the sphere, and that would control, you know, also how high you would have to go in this polynomial. So I don't know how to write down a formula for flat space, but I suspect that the formula will involve, you know, blank scale divided by radius of the sphere divided by blank length, number of operators, and you should be able to write down a similar formula. You should really be able to write down a formula in canonical gravity. This is not a new effect I'm postulating. You know, nowhere in any of this did I postulate any new physics. All of these were, you know, this was the Richter theorem, and this came from just using the fact that the Hamiltonian was a boundary term, which is just coming from canonical gravity. So I'm not postulating any new physics here. So it sounds surprising, but it's not doesn't involve any new physics. It should follow just from ordinary gravity, quantum gravity canonical gravity that we know about.
that we should find non-local effects.
That we should find these, that we should, but you know that these effects already exist because we don't have any notion of local gauge invariant operators in gravity. There is no operator which is localized, which is completely gauge invariant. So it's, you know, when you say that you should find non-local effects, the point is in gravity you can't define locality because you don't have any notion of a local gauge invariant operator. Every gauge invariant operator you write down has to have some Wilson line that goes out, and so it's not, you know, because you have to frame it with respect to some point. And so it's not surprising that you try to act with an operator here and you can detect it from the boundary. That's because you don't have local gauge invariant operators. All operators look like they have a Wilson line, and it's that Wilson line that you can detect by going out. You have to work very hard to detect it, but you can. You know, it sounds surprising because we think of the light cone because we think of local gauge invariant operators, but in gravity there is no such thing.
Okay, good. Let's thank once again.